lecture. Welcome everyone for today's special quantum space-time seminar. Professor Edward Witten from IAS has very kindly agreed to give us the continuation of his Madan Lal Mehta lecture on black hole thermodynamics then and now. So we welcome you to the same. Over to you, Edward.
Thanks so much for the invitation. So I'm going to just first take a moment to recall where we were at the end of the first lecture. So we discussed the Bekenstein bound, which says that a quantum system of entropy E, size R, and entropy S is supposed to obey a universal relation where E times R is bounded below by constant times S for some universal constant K. The bound has the property that it's trivial when the usual conditions for validity of thermodynamics are applicable, at least if you only consider ordinary matter in the real world. It's only interesting if it's supposed to apply to every quantum state. So we can't interpret the S in the Bekenstein bound as thermodynamic entropy. It has to be some sort of entropy that makes sense for any quantum state. So such a concept is the von Neumann entropy, which is the entropy of the density matrix rho that describe. So if you have a quantum state described by density matrix rho, its von Neumann entropy is this minus trace of rho log rho. Now, if a system is truly in thermal equilibrium with the usual thermal density matrix, where I shouldn't here have written the trace, the density matrix is what I wrote without the trace, then the von Neumann entropy is equal to the usual thermodynamic entropy. So if entropy means thermodynamic entropy, then you could use von Neumann entropy instead. But the von Neumann entropy is more general. It's always defined for any quantum system. When we say a system is thermalized, we don't normally mean literally that its density matrix is a thermal one, which is very hard to achieve for a macroscopic system. We mean that simple accessible measurements don't distinguish rho from rho thermal. There's some feedback somewhere. I don't know where it's coming from. Possibly some.
Yeah, I think it's better if the rest of the audience mute themselves unless they want to ask a question.
So when we say that a system is thermalized, we mean that a simple measurement can't distinguish the density matrix from a thermal one. In such a system, the microscopic von Neumann entropy might be less than the thermal entropy, possibly much less. For example, if you have a system of qubits, which would have 2 states per qubit, but you only fill 2 states for every other qubit, then your von Neumann entropy is half of what it could be thermally. But if the number of qubits is extremely large, the number of states is so large that no reasonable measurement would learn that you've only filled 2 to the 1/2 n states instead of 2 to the n states. So the thermal entropy is the largest the von Neumann entropy could be, given what you know about a system by simple measurements. But the von Neumann entropy itself can very well be much less. The thermal entropy is what you get if you coarse grain and approximate the actual density matrix as a thermal one. So a most basic difference between the 2 kinds of entropy concerns the second law. Consider, for instance, an isolated system, say a fluid in a box, initially in an inhomogeneous state. It undergoes unitary evolution with a Hamiltonian H. Such a unitary transformation doesn't change the eigenvalues of the density matrix, so it doesn't change the von Neumann entropy. So there's no second law for the von Neumann entropy of an isolated system. That von Neumann entropy is simply constant. What about the thermodynamic entropy? Initially, simple measurements could reveal the pressure P and temperature T as functions of position X in the box. And assuming that's all we can learn from simple measurements, we define the thermodynamic entropy as the integral over the box of the entropy density as a function of P and T. After a while, the fluid thermalizes and simple measurements would reveal less, basically only the average temperature and pressure. The thermodynamic entropy will have increased. It will be what you would have in pure equilibrium because of coarse graining over microscopic information that's effectively lost when the system thermalizes. Let's ask what kind of entropy is the generalized entropy of Bekenstein, which is the area over 4G h bar plus the entropy outside. Last time I left out the h bar in this formula, setting it to 1. but today I'll try to remember to include it. In Bekenstein's interpretation, the area term represents coarse graining over unobserved internal structure of the black hole, so we should interpret it as thermodynamic entropy. And of course, the area can increase when the black hole grows. Bekenstein proposed a generalized second law that the generalized entropy, the area over 4G plus the ordinary entropy outside the black hole, can only increase. Is it true? Well, remember, the classical limit of the statement is the Hawking area theorem of classical general relativity. Well, I even will sketch the proof later, actually. So classically, for a black hole, the area is non-decreasing. Whenever we're near a classical limit in which the black hole is absorbing matter, the generalized second law is true because GH bar is so small. So whenever dA dt is non-zero in a classical limit, it's much bigger than the change in the entropy outside, no matter what you mean by the entropy outside. So the only interesting case for the generalized second law is the case where classically dA dt is 0. So to challenge the generalized second law, we consider a stationary black hole like a Schwarzschild black hole, so that classically dA dt is 0. We let the black hole interact with quantum fields and ask what happens to the generalized entropy. What must we mean by the entropy outside if the generalized second law is to be true? If the quantum fields are in a state such that thermodynamic entropy makes sense, we'll be back in a situation where the generalized second law is easily satisfied. The kind of estimates we made last time would be applicable. The challenge is to ask if the generalized second law is true for an arbitrary state of the quantum fields outside the black hole, one for which thermodynamics wouldn't apply. In this generality, we have to use a notion of entropy that makes sense always. So the version that makes sense is the microscopic or fine-grained entropy of the density matrix rho out that describes quantum fields outside the horizon. So we have to interpret the outside entropy to be the von Neumann entropy outside the black hole, which is minus the trace of rho out log rho out. With this interpretation of what we mean by S out, both terms are ultraviolet divergent. Unfortunately, I left Newton's constant in the first term, left it out here. But the first term is ultraviolet divergent because there are divergent quantum corrections to Newton's constant. And last time we discussed that the second term is ultraviolet divergent because of short distance fluctuations near the horizon. But Susskind and Uglum showed that the divergences cancel, and S gen, with this interpretation of what you mean by S out, is ultraviolet finite in perturbation theory. So that's another reason that S out has to be the von Neumann entropy. So, well, should we expect that for an arbitrary quantum state with thermodynamics not being applicable, the generalized entropy is always instantaneously increasing at every time? I wouldn't have been sure that the answer to that question should be yes, even if the generalized second law was in some sense true. Perhaps this is too ambitious a version, but as I'll explain, it was shown by Aaron Wall that this strong statement of the generalized second law is true. But before we do anything fancy, let's just ask what happens to the generalized entropy when a black hole, all alone in empty space, is emitting Hawking radiation. So as the black hole emits Hawking radiation, it shrinks, the area term goes down. On the other hand, it's emitting radiation, and we have to include the entropy of the outside radiation, which is going up. So what happens to the generalized entropy? The answer is that the generalized entropy increases. For a black hole to emit radiation at temperature, Hawking temperature, TH, into the vacuum, while the vacuum has temperature 0, is a thermodynamically irreversible process, so it should be increasing the entropy. And as we'll now discuss, it does. A careful estimate was done by Don Page in the 70s. I'll give a simple estimate. During a time delta t, the black hole emits thermal radiation that fills a shell of thickness L equals delta t times the speed of light, c. So here's our black hole. And in gray, I've sketched the radiation that fills a shell that was emitted during a time delta t, delta tau. So we're going to compare the thermal entropy of this shell to the change in area of the black hole while the shell was emitted. So let n be the effective number of partial waves in which the outgoing radiation is emitted. Now, because of an angular momentum barrier that we didn't discuss last time, there's an effective cutoff of the angular momentum of an outgoing mode. And it's a smooth cutoff, so that's why I say Don Page made a careful estimate. But we won't do that. We're just going to say that there are n partial waves in which outgoing radiation is emitted. Now, then effectively, the shell contains n modes of a 1+1 dimensional massless chiral field at the Hawking temperature. Now, using the standard formulas for the energy and entropy of a 1+1 dimensional ideal gas, the standard formula is that for n modes, this is sometimes written in terms of C rather than n, but a single mode, n modes would have central charge C. So for n modes, the central charge, the entropy is pi times n/6 times T, and this is the energy. And so the change in the energy and entropy of the radiation during time tau are given by relating these two formulas. So comparing these formulas, you see that the change in the energy is the Hawking temperature over 2 times the change in the entropy. And reciprocally, the change in the entropy is 2 over the temperature times the change in the energy. You could have gotten the factor of 2 between the, see, the point is that one formula has a 1/6, one has 1/12. You could get that by integrating dE equals TdS, where you adiabatically create the ideal gas at temperature T Hawking by adiabatically increasing the temperature from 0. At 0 temperature, E and S are both 0. And if you integrate dE equals TdS from 0 up to T, you'll find that this formula with the 1/6 implies this one with the 1/12. And therefore it implies a factor of 2 in the relation between the entropy and the energy. Conservation of energy says the energy gained by the radiation is the energy lost by the black hole. So delta E of the black hole is minus delta E of the radiation. The black hole is emitting radiation adiabatically, so the change in its energy and entropy are related by this. So in other words, the change in energy of the black hole, integrating this formula over a time interval small enough that the temperature is constant, it says that the change in energy of the black hole is the Hawking temperature times the change in entropy, or the change in entropy is 1 over the Hawking temperature times the change in energy. But we compare this with what happened to the radiation, which had a factor of 2. So we learn that the entropy change of the radiation is minus twice the entropy change of the black hole. In other words, the entropy gain of the radiation is twice the entropy loss of the black hole, reflecting the fact that for a body to radiate at temperature TH into the vacuum at temperature 0 is thermodynamically irreversible. That's encouraging, but can we give a completely general proof of the generalized second law for a stationary black hole interacting with quantum fields in an arbitrary state? And this is a proof that the generalized second law holds instantaneously at every time. Yes, we can, as shown by Aaron Wall, provided, again, that S out is the von Neumann entropy of the density matrix of quantum fields outside the horizon. We're going to use as a tool the same relative entropy that we used in discussing the Bekenstein bound. Recall that the relative entropy between two density matrices, rho and sigma, is defined by this little formula. And the only fact we used about it last time was the fact that it's non-negative with equality only of rho equals sigma. For the generalized second law, the key is a deeper property closely related to strong subadditivity of von Neumann entropy. And the version of it we'll use is the following. Suppose that U and V are two regions of space with V contained in U. Let rho U and sigma U be the density matrices of two states of a quantum field for observations in the region U, and let rho V and sigma V similarly be the density matrices of the same two states in region V. Then the relative entropy in region V is less or no bigger than the relative entropy in region U. So I'd love to explain the proof today, but it's a little bit too long. My version of the proof is in section 3 of this article on the archive. It's simple. I can assure you, if you look at it, you'll find it relatively painless, but I reluctantly decided not to try to explain it today. So we're going to apply this for two regions, U and V, but what will the two regions be? Well, here's again a picture of the black hole that formed from collapse. So the red is the part of space-time filled by the collapsing star. The horizontal line is the black hole horizon. This other horizontal line is future null infinity. The past infinity is down here, and this corner of the picture is spatial infinity. And the spatial region we'll consider is a region U that goes from a cut of the horizon to spatial infinity. So the point is that any observer who stays outside the black hole horizon for all times will eventually pass through this cut. So this cut will capture, roughly speaking, everything that there was outside the black hole at the time where we made the cut. See, the time where we make the cut here is an invariant, but if you move U back and forth, keeping this time fixed, then it'll capture the same stuff. So the region U is appropriate for measuring the generalized entropy at a time defined by a cut on the black hole horizon, not a time defined at infinity. Nothing would change if we change the time at infinity, which would be by unitary evolution by the Hamiltonian at infinity. But the generalized second law will say that if we make a later cut, so here's a later cut. The generalized second law will say that if we make a later cut, the generalized entropy is no smaller. Now, in what sense is the later cut a smaller region? So here are the two pictures. Here's our earlier cut, here's the later cut. We want to say that the later cut is a smaller region. One way to look at it is that the initial value surface with the later cut has a smaller domain of dependence. If you know nothing except the quantum fields on this partial Cauchy surface U, you could predict what there is in the green region, which is the domain of dependence of the region U. You see, you can't predict what there is here because it might fall into the black hole and never reach U outside the black hole. But if you know what there is on the surface U, you know what there is in the green region of spacetime. If you know what there is in the later cut, you have a smaller domain of dependence. So one sense in which U is V is a smaller region is that it has a smaller domain of dependence. Another technically useful answer is the following. We could describe the same space-time region, not with this partial Cauchy surface U, but with a different one, which hugs the horizon plus future infinity outside the horizon. In other words, we replace U with this region. Well, it's another, I've drawn it in green now. I've still labeled it U. You see, this green region, a knowledge of the physics here, would enable us to predict physics in exactly the same spatial region that this surface does. So it would be equally good to predict, well, to have complete access to what there is in the future outside the black hole, that's here, plus what there is on the horizon after a certain time, a certain cut of the horizon at a certain time. Well, a certain time t is measured on the horizon. So with this interpretation, the later cut just corresponds to a smaller initial value surface. Here's the cut at one time. Here's a cut at a later time. So one is simply a smaller initial value surface than the other. So it's a smaller spatial region. And we can use that principle that for a smaller region, the relative entropy will be less. So this makes it obvious we can use the inequality for the relative entropy. Now, rather as last time, we expand the relative entropy as a sum of two terms. One, which is the trace of rho log rho, is minus the entropy of a density matrix rho. The other term, last term we interpreted as a kind of energy term, so I'll call it E. So the relative entropy will be, I'll call it E minus the entropy of the state rho. And rho is going to be the quantum state in which we're trying to prove the generalized second law. So the generalized second law is supposed to hold for every density matrix, and so we'll try to prove it for rho. Sigma will be chosen conveniently so that we can say something nice about the energy term. So S of rho will be S out. And the inequality about the relative entropy will say that S out on surface V minus the energy on surface V is S out on surface U minus the energy on surface U. So the difference of the two S outs, I'm calling delta S out. And this inequality will tell us that something plus delta S out is non-negative. What we want is that delta area over 4GH bar plus delta S out is non-negative. So the inequality we have will be the one we want if we can pick the state sigma so that with the help of the Einstein equations, the energy difference is the area difference times -1/4gh bar.
Sorry, Edward, may I ask a small question, please?
Yes.
The Penrose diagram you drew was for a non-evaporating black hole. I suppose if you include evaporation, the same statement about U and V being respectively bigger and smaller will go through.
Actually, we will include evaporation. What evaporation means is that evaporation is a property of the quantum state around a Schwarzschild solution. So we're going to discuss the stress tensor of the quantum field in an arbitrary quantum state. And that will include the contribution of to the stress tensor of the radiation. So we're going to be computing effects of order h bar that will affect the geometry. And that will include Hawking radiation.
Okay, so you'll keep the geometry, what you drew, and then compute the stress tensor.
Yes, okay. Well, at h bar equals 0, we have some geometry.
Right.
Then we'll turn on quantum effects. It will cause a correction to the geometry and we'll calculate the correction. Okay. So we'll have a quantum corrected geometry, which will differ from the classical picture by corrections of order h bar. Mm-hmm. And in particular, the area will change by an amount of order h bar. Mm-hmm. And what we want to know is that the change in the area over 4gh bar plus the entropy outside is non-negative. Okay. So the input is the classical geometry plus the quantum state. The quantum state determines the entropy outside. Mm-hmm. Then we'll use Einstein's equations together with properties of the state to determine the change in the area. So we'll be computing the change in the generalized entropy in a way that includes the Hawking radiation. And if the outside state, well, if you took an outside state with no incoming radiation, I forget what it's called, maybe the Unruh vacuum, but I'm forgetting right now. If you took the right outside state where nothing is happening except Hawking radiation, our calculation would literally give the change in the geometry due to the Hawking radiation. You'll see that as we proceed, perhaps.
Okay, thank you.
Just to clarify, like if the black hole is evaporating, I'm confused whether why is the domain of dependence of V always smaller than U's? Because a later cut would have a smaller event horizon, right?
Yeah, that was partly my confusion too.
Well, in the classical limit, they're smaller.
Yeah.
We're going to do the computation in the back classical geometry.
Yeah.
So this is okay. Okay. We want to evaluate this inequality to order 1. So since the area term has a 1/h bar in it, we need to know delta area to order h bar. But we only need to know the change in the von Neumann entropy to order 1. And that means the von Neumann entropy is anyway of order 1. So we don't have to worry about the change in the geometry and correcting the von Neumann entropy, because that would be of order h bar. So when we discuss the entropy term in the formula, we use the classical geometry. But then we will use the
and order h bar correction in the geometry would give an order 1 correction to the generalized entropy, right?
An order h bar correction to the area will give an order 1 correction to the area term because there's a 1/h bar in the area term. So an order h bar correction to the geometry will do nothing to, we'll change the entropy by order h bar, which we won't worry about, but it will change the generalized entropy in order 1 because the generalized entropy starts in order 1/h bar. Is that clear, or are there more questions?
Yeah, thanks.
Sorry, Edward, one question.
Yes.
So you offered this intuition when the black hole radiates into vacuum that radiating to this would be a thermodynamically irreversible process because you're radiating it T equal to 0. But what if the temperature of the matter fields outside is higher than the black hole?
Well, then it's the opposite.
How does one?
Then it's the opposite. Then the black hole will grow. Okay. Since there's you could repeat. I think you could repeat the discussion we did, and you'll see the generalized entropy still increases. You expect it to increase because for the black hole to be in contact with thermal radiation at a higher temperature is also thermodynamically irreversible. So now what will be happening I think you'll see the same factor of 2 will work in your favor again. If you repeat the analysis for the case that the black hole is interacting with radiation at a higher temperature. In that case, the radiation in that shell we had will be going in instead of out. Or radiation at a high temperature will be going in, and the shell will be filled by radiation at a lower temperature going out.
Okay.
I think you'll see it works. Well, that's a good question, actually. I hadn't thought about it, so I'm answering off the cuff.
Okay, thanks.
Any other questions? So our goal will be to show that the difference in energy terms is a multiple of the difference in change in area. So what we need to do is to understand quantum fields in a null plane. The reason we need a null plane is that the horizon is a null surface. So there are some facts about quantum fields on a null surface which were essential in Aaron Wall's discussion of the generalized second law. So we'll start with the null surface in Minkowski space. So the metric I'll take to be minus du dv plus dx squared. And I'll take n to be the null plane where u is 0. And then remember, we wanted to cut the horizon at some time. So the null plane is parameterized by v and also by spatial coordinates x, which I've drawn horizontally, although not labeled. So I'll cut the horizon first. I'll cut n, first of all, at v equals 0. That's one cut. And so I could consider the green region, and roughly its domain of dependence, if we're above 2 dimensions, of the portion n plus is meant to be the green region up here. So the portion of Minkowski space where you could be pretty sure that anything in there will flow through here is a Rindler space. I've drawn only u and v coordinates in this picture. I haven't drawn the normal coordinates x. So you see, anything in this Rindler space will eventually pass through the ray v equals 0. To avoid it, it would have to be moving precisely parallel to that ray, which if we're above 2 dimensions is a set of measure 0. So although the Rindler space doesn't technically satisfy the definition of a domain of dependence, it has the same property that anything in the green region will pass through it. Now suppose we're only able to make observations along n above the cut. Well, that's equivalent to making observations in the right Rindler space. And we learned last time that the density matrix that describes such observations in the vacuum state omega is sigma was the exponential of minus 2 pi k, where k is the Lorentz boost generator on the null plane. Well, to be more precise, this is a partial Lorentz boost generator that boosts fields in the right Rindler space, does nothing in the left Rindler space, and does something complicated in the future and past wedges. This is a Lorentz boost generator if you're living in the right Rindler space, but that's not what it is if you're living somewhere else. The reason for that is that we've integrated from 0 to infinity, not from minus infinity to infinity. Now we want to generalize this for a general cut of the null plane of the form v equals f of x for an arbitrary function f. So here, with x running horizontally, I've drawn a curve v equals f of x, and now the green region is for v bigger than f of x. So it's a wiggly cut of the null plane, and let n plus comma f be the region where v is no less than f of x. The domain of dependence of n plus f is a wiggly generalization of the Rindler region, but I'm not going to try to draw it. I'll leave that for better artists. Now, to find the density matrix that describes measurements in n plus f, or equivalently in its domain of dependence, we're going to use the symmetries of operators on the null plane. The point is that the operators on the null plane have symmetries that aren't symmetries elsewhere. First, consider the operator p that simply generates translations of v. It's the integral over the null plane, which I'm calling n. This h is a misprint of tvv. It annihilates the vacuum, and it's strictly positive on all other states. It generates translations of operators on the null plane and, of course, all other operators. This one is a symmetry, a true symmetry, so it generates translations of all operators, but in particular, it shifts the position of an operator on the null plane by a constant f. Now instead consider a similar operator, p sub f, but with a non-constant f. Well, we're going to use this operator to map the cut at v equals 0 to the cut at v equals f of x. P sub f is not a symmetry operator. It doesn't commute with the Hamiltonian, and off the null plane, it probably does very complicated things. But on the null plane, it's simple. First of all, the null translation P and the Lorentz boost K, and here I mean the true Lorentz boost, the exact symmetry of the vacuum, they have simple commutators with P sub f. So a translation that adds a constant to V commutes with P sub f, and a Lorentz boost rescales P sub f. These properties imply that P sub f annihilates the vacuum. So first of all, since P sub f commutes with the null translation P, it doesn't change the eigenvalue of P. And since the vacuum is the only state of P equals 0, therefore P sub f has to be a multiple of the vacuum. But if you assumed a non-zero eigenvalue, you'd run afoul of Lorentz invariance, which would, after a little while, show you that P sub f can be rescaled, so the eigenvalue has to be 0. So P sub f must annihilate the vacuum. Any questions on that? Because it's a key point, actually. So P sub f isn't a symmetry of the theory. It doesn't commute with Hamiltonian, but it is a symmetry of the vacuum. The key point is that e to the I P sub f conjugates operators on the region n plus above the v equals 0 cut to operators on the region above the v equals f cut. If f were constant, P sub f would just be f times P, and we'd have this simple formula. Since f isn't constant, there are additional terms involving derivatives of f. But every time you differentiate f, the dimension of the operator goes down by 1. So the OI are operators with dimension 1 less than the dimension of O. I really should have written the argument of OI. The argument of OI is the same as the argument of O, namely v sub f comma x. And likewise, these other operators OIJ have dimension 2 less than that of O, but they're evaluated at the same point, v plus f and x. And this series stops after finitely many steps, assuming that the operator O had finite dimension. So it's a finite series since after finitely many steps, we'd be getting operators of negative dimension. I'm assuming our theory is either conformally invariant or at least asymptotically free in the ultraviolet so that we can make sense of the dimension of an operator as measured in the ultraviolet. The important point here is that conjugation by e to the IPF maps observables in the flat null half plane to observables in the above the cut region n plus f. It doesn't do it in the simple way that you get if f is constant. There are corrections involving derivatives, but they stop after finitely many terms. To derive this formula, you could expand e to the IPF. You could expand this in a nested series of commutators. And sometimes the commutator can lower the dimension. That can only happen finitely many times because you'd reach 0. If the operator isn't lowering the dimension, it's generating a translation in the null direction. So in the series of nested commutators you'd get translations by an amount f, and occasionally that would be interrupted by operations that lower the dimension. So in general, you'll get something like this. In a free field theory, you can compute exactly what are the higher terms in the formula. For a simple operator, actually, it stops after this term. Now, we've learned two facts. One is that the operator e to the IPF leaves the vacuum state invariant. The second is that conjugation by e to the IPF is an isomorphism between the algebra of observables in the region above a flat cut and the algebra of observables above a wiggly cut of the null surface. Combining these facts, conjugation by e to the IPF will map the density matrix sigma 0 for observations in region n plus to the density matrix sigma f for observations in region n plus f, like so. But we know what sigma 0 is. And so the logarithm of sigma 0 is just minus 2 pi times the partial boost operator k. So the logarithm of sigma f is just gotten by conjugating this thing by e to the IPF. And using the commutator that we had between k and pf, we learned that the logarithm of sigma f is just minus 2 pi to what we could call k sub f. That's, well, this, sorry. So k sub f is defined similarly to k, except that instead of integrating over v bigger than 0, you integrate over v bigger than f with a factor of v minus f instead of the factor of v. So to summarize this page, the fact that the operator e to the IPF leaves the vacuum invariant and maps one algebra to the other means it conjugates one density matrix to another. So it conjugates the logarithm of one density matrix to the logarithm of the other. And what I did was just to conjugate this by this and got k sub f. So we have an explicit formula for the logarithm of the density matrix for observations above a wiggly cut. Now, a small generalization of this formula plus some discussion of Einstein's equations will lead to the generalized second law. But before going there, I want to explain a heuristic derivation also due to Wall of this result. The idea is that operators on different null lines on the null plane are at spatial separation. So there's no causal relations between them. They commute with each other. So I've drawn some null lines in red on this null plane. They're space-like separated and commute. As far as the construction of the Hilbert space is concerned, the theory in the null plane is like an infinite, tensor product of 1 plus 1 dimensional theories, parameterized by the normal directions. In each of these theories, at any given x, f is just a constant, because on each null line, f is just a constant. So on each null line, e to the IPF is the same as e to the IP, except with a different origin of the coordinates. So it conjugates the density matrix by v going to v plus f. So then we get log sigma f by integrating the resulting formula over k sub f. As Wall explained, if it's possible to make a lattice regularization of the theory in the x directions while maintaining 1 plus 1 dimensional Poincare invariance, then this argument becomes rigorous. Now we need to navigate toward the application to black hole horizons. So first of all, the black hole horizon is a null surface swept out by light-like geodesics that are called the horizon generators. So since the black hole horizon is null, it has a null coordinate, which I'm calling v. And null means that there's no dv squared term and there's no dv dx term. Changes in v at fixed x are simply null vectors. So the metric of the horizon looks like this, in general with a spatial metric for the x's that depends on v. For example, if the black hole is growing, GAB will certainly depend on v. We can determine v almost uniquely by asking for it to be an affine parameter along each null geodesic.
Sorry, Edward, one question.
Yeah. Yes.
So why was it important that this series terminated after finitely many terms?
Well, otherwise you'd lose control, possibly. In other words, an infinite sum of operators might not be well defined. The reason I'm sure this formula is true is that it's a well-defined series with a finite set of operators in it. You see, when you derive this formula, suppose you discretize this e to the IPF. So you think of it in terms of many, many steps. I can't see my camera at the moment, but I hope you see it so you can see me. So
yeah,
there are many, many steps, and you try to push O of Vx forward in time many, many times with very small steps. Finitely many times that won't work, and instead the dimension will go down, but all the other times you'll move forward. Since there only are finitely many misses, it's obvious that you'll end up moving forward by the same amount as if there were no misses in the limit that the number of steps, that the size of the steps goes to 0 and the number of steps goes to infinity. But if you could have infinitely many misses, it would be less obvious.
Mm-hmm.
So these lower terms are a little bit like having derivatives in the v direction. And a finite series of v derivatives of O is still a local operator at O, but an infinite series may not be. Is that clear?
Yes, yes, thank you.
Okay, so we're going to have to generalize this formula for a black hole. Sorry, I did explain the heuristic argument already. Okay, so we're here. So this is the general form of the metric of the horizon, where the only input I've provided is that it's null. It's a null surface. So there are what are called the horizon generators. They're null geodesics on the horizon. And I've chosen V so that the horizon generators are parameterized by V and labeled by the x's. And then we can normalize V to be an affine parameter on each null geodesic. Now the metric GAB on the horizon is not arbitrary. This is completely crucial. It leads to the Hawking area theorem, and it's about to lead to the proof of the generalized second law. The metric on the horizon is not arbitrary. It must obey a constraint equation, which is the null analog of Ricciardori's original equation. This null equation is just the VV component of the Einstein equation. It's the equation GVV, where G is the Einstein temperature, the Einstein tensor, is 8 pi G times TVV. To analyze it, it's convenient to set bold A to be the square root of the determinant of G. The reason I call it bold A is that it's a little area element. If you integrate bold A over the horizon, you'll get the area capital A of the horizon. And then it's conventional to write theta to be A inverse dVA. Then the Einstein-Ricciardori-Sachs constraint equation, which is just this equation, is a first-order equation for theta. But the important thing about it is that it only involves derivatives on the horizon, not off the horizon. So it's a constraint on initial data on the horizon. That happened because general relativity is a gauge theory, so initial data are subject to constraints. And this is the important constraint on initial data on a null surface. Actually, on a null surface, I think it's the only constraint. Now, before applying this constraint equation to the generalized second law, since we've got it, I'm going to explain how it leads at the classical level to the Hawking area theorem, which is the classical limit of the generalized second law. I just write the formula again, but I have it already, sorry. I write it in the same form. The point is that everything on the right-hand side is negative, by virtue of which you can prove that if there's anywhere on the horizon with theta less than 0, theta will go to minus infinity at a finite v. For example, suppose theta equals minus epsilon at some time v. Well, it'll be less than minus epsilon at all times because the derivative is negative. And it'll be less than it would be if you threw away these terms because they're negative. So you could get a lower bound on theta for all times by just solving the equation with the first two terms only. And if you do that with initial condition that theta is minus epsilon at v equals v0, you'll find that theta goes to minus infinity at finite v, which you can show as a contradiction. That last step isn't completely trivial, but the Hawking area theorem is completed by proving that it's a contradiction for theta to go to minus infinity at finite v. So you see, once you know that theta can't go to minus infinity at finite v, since it would if it's anywhere negative, it follows that theta is everywhere non-negative. But since theta is A inverse dVA, theta being non-negative means that the local area density is everywhere non-decreasing. And the black hole area is simply the integral of little a. So little a having a non-zero derivative means that the area is everywhere increasing. So anyway, that's essentially the proof of the Hawking area theorem, except that we have to more carefully discuss why this step is a contradiction. Now, in our study of the generalized second law, we want to consider a horizon that classically has constant area and study the quantum effects. So, well, what would make the area constant classically? Well, we can learn that again from the same constraint equation. To make the area constant classically, theta should be 0. But since all these terms on the right-hand side are negative, they have to all individually be 0. So theta should be 0 and also sigma AB should be 0. I think I forgot to say what sigma AB is. It's the traceless part of the derivative of GAB. So theta and sigma AB being 0 means that the V derivative of GAB is 0. So the horizon metric is stationary. it's independent of the null time V. So the case of a black hole that isn't growing classically is the case that the shape of the horizon is V independent, time independent. If there's any dynamics at all in the horizon shape, then the horizon is also growing in area. Now we want to turn on effects of order h bar. That means in the constraint equation, we need to consider effects of order h bar in TVV. So there are some quantum fields outside the horizon. And they contribute. Yes?
One question. So why is it that imposing that the total area should be constant implies the local change should be, that there should not be any local change? I mean, it could be that the integrated area remains constant.
It follows from the Ricciardori equation. So here's the Ricciardori equation. Okay, I use without telling you explicitly that for physically sensible matter, TVV is non-negative. That's all physically sensible matter has non-negative TVV. So everything on the right-hand side is negative. Then I explain the proof of the Hawking area theorem. If theta is anywhere negative, it will go to minus infinity in finite time. The step in the proof of the area theorem that I skipped was to show that that's a contradiction, but it is. Once you know that theta is non-negative everywhere.
Right.
To make theta, so now, okay, the only way that the area can then be non-increasing is if theta is everywhere 0.
Yeah.
Because since theta is nowhere negative, if it's anywhere increasing positive, then the area is increasing.
Yes, thank you.
To make the area constant, the theta dv has to be 0, and then everything on the right-hand side has to be 0.
Yeah.
And that means that the derivative of the metric has to be 0. So the horizon metric is only a function of the x's, not v. The horizon shape has to be constant classically if its area is constant. Now we're going to turn on effects of order h bar. And in the constraint equation, the expectation value of TVV will be of order h bar. So everything will be corrected in order h bar, and in particular, theta will become order h bar. We need to keep track of orders of h bar in this formula. Since theta was 0 classically, theta squared is of order h bar squared, and we will ignore it. If the only quantum fields you consider are matter fields, then sigma would also be 0 classically and of order h bar, and then this term would be of order h bar squared. There's a subtlety that if you want to include in this gravitons, it turns out that sigma AB has a graviton contribution, a contribution bilinear in graviton fields that's of order h bar. So we can't ignore this term, but it's analogous to TVV. It's the you can think of it as the graviton contribution to TVV.
Can I ask a question, Edward?
Yes, in a second, but let me finish one more sentence.
Yes, please.
So we're going to simply ignore this term, thinking of it, including it in this term as the graviton contribution. Go ahead.
Yeah, so are you thinking of this equation, continuing in the quantum theory as some kind of an operator equation? And
Yes.
I see. So
we don't have to understand it too deeply, though. We'll just take the expectation value of this equation. So we're going to assume that to order h bar, we can take the expectation value of TVV in a quantum state, and then solving this equation with that source will give us the order h bar back reaction on the geometry.
But in principle, there could be some operator counter terms to keep the equation valid, or that kind of.
Well, there are because TVV needed normalization to define it.
Yeah.
We're going to assume that TVV was correctly defined in the quantum field theory.
Okay.
The graviton contribution. If you include gravitons, then we'll assume that sigma AB was properly renormalized to get the graviton contribution to TVV.
I see. Okay.
So renormalization has been made before we take the expectation value of this equation. Then we will assume, we ignore the theta squared term, but we'll assume that the order h bar correction to d theta dv can be gotten by taking the renormalized stress tensor in the quantum state.
Nice. Okay, thank you.
Whether you can extend this to higher orders in H bar and what would be involved, I can't tell you. I think it's highly, I mean, it's a good question, but I think it's highly plausible that this procedure is correct. And it gives such a beautiful answer that I'd conclude it must be correct. But we'll see that in a moment.
So just follow up the thing that in these various island papers, sometimes one takes a sort of large number of matter fields so that the quantum corrections themselves become of order 1. And then
Of order 1, but small.
order 1, yeah, that's right.
So you could do the following. You could take n quantum fields,
Right.
where n is large and h bar is small, such that n times h bar is non-vanishing as h bar goes to 0, but small. And then your expansion parameter would be n h bar rather than h bar.
Yes, right.
If you try to make n h bar of order 1, the discussion would break down. But I think the discussion still makes sense if n h bar is, as long as n h bar is small.
Okay, got it. Thank you.
If you do that, then the sigma AB term is unimportant because it is only one quantum field, or 2 if you count 2 helicities of gravitons in 4 dimensions.
Right. So then it's only the TVV.
Yes.
Right.
But I think it's believed, but I'm not sure it's been carefully demonstrated, that the sigma AB term can be treated as a graviton contribution to TVV. In other words, the statement is that it's what you'd expect the graviton contribution to be. Perhaps that's been demonstrated carefully. I haven't seen it, but I don't know all the papers. Now, since A is constant classically in the situation we're interested in, dVA and dV squared A are both of order h bar. So since theta was defined as A inverse dVA, dV theta is dV of A inverse dVA. And it has 2 terms because dV could act on either A here or A inverse. But the term where it acts on A inverse is of order h bar squared. So the only term we need to keep is this one. So the expectation value of the equation becomes this. I dropped theta squared and sigma squared, and I substituted this for dV theta, and then I multiplied A inverse to the right-hand side. And also I've put labels. So A classical, so first of all, the expectation value, TVV, I took its expectation value in the quantum state of the system, but I replaced, well, see, since TVV is of order h bar on the right, I took the classical value for A classical. On the left, if I use the classical value, the derivative is 0, so I simply, on the left, replace A by its quantum correction AH bar. So we get this nice equation for the AH bar in terms of A classical and the expectation value of TVV. So to answer one of the questions we had some time ago, this expectation value of TVV does include a negative term if there's Hawking radiation. Okay, whenever Hawking radiation is the negative, is the dominant effect, TVV is what it would be just from Hawking radiation. So now we solve this equation and we pick the solution that has sensible behavior as V goes to plus infinity. And the solution with sensible behavior for V going to plus infinity is this one, up to a possible additive constant independent of V that won't be important when we compare 2 different cuts. So then we integrate over transverse coordinates. And since the area is the integral of little a, we learn that the order h bar term to the area A on the cut at F is given by this formula. Minus 8 pi g times an integral over the region above the cut of V minus F times TVV. And that's a quantity that we saw before when we discussed density matrices above the cut in Minkowski space. Okay, but before we get there, so the order h bar, well, the order 1 contribution, what I've written, okay, this is true as written, but I wish I divided it by h bar. The order h bar contribution to A over 4g along the cut is this. I just divided this equation by 4g. So except for 1 over h bar, this is the correction to the area term in the entropy. Now suppose there's a state whose density matrix sigma f in the region above the cut satisfies the same formula we had in Minkowski space, that the logarithm of the density matrix is minus 2 pi times this integral. We'll find that state in a moment. Then the order h bar contribution to the black hole entropy measured on the cut. Well, you see, I just assumed that there's a state such that the expectation value of log sigma in that state is this integral. And if it's true, then the order h bar, then the quantum correction to the area term in the entropy is just a trace of rho f log sigma f, where rho is the density matrix in the region above the cut for the state that the system is actually in, and sigma is some convenient state chosen so its density matrix sigma f satisfies this formula. So in other words, if there's a state whose density matrix sigma f is this, then the formula for the quantum correction to the area can be written in terms of the log of sigma f, its expectation value in the quantum state, whatever it is, which is the same as the trace of rho f times log sigma f. In that case, the relative entropy for the two states rho and sigma for the region n plus f is trace rho log rho minus rho log sigma, and that'll be minus the entropy minus the area over 4gh bar. In other words, the relative entropy will be minus the generalized entropy, plus a constant that we threw away when we, the one constant is the classical term, and also we threw away a constant when we solved Ricciardori's equation. Now suppose we have two cuts, g and f, with g to the future of f. I've drawn the horizon differently. I've drawn v running vertically, even though it's in null direction, because we're thinking of it a little bit as time, and a spatial cut of the horizon I drew horizontally. And I tried to capture the idea that the horizon geometry classically is independent of v. I hope this picture is big enough you can see it. On my screen, it's a little hard to see. Well, monotonicity of relative entropy says that the relative entropy on the surface on the earlier cut is bigger than it is on the later cut. And since the relative entropy is minus the generalized entropy, that's the generalized second law in the opposite direction, but the generalized second law on the later cut is no less than the generalized second law on the earlier cut. So to finish the argument, for a general stationary horizon, we need to find a state sigma such that for any region above a cut, the reduced density matrix satisfies this nice formula. Now, we've already done this for a Rindler horizon, which is the case that the XA parameterized RD minus 2 with a flat metric. Now we need to extend to the general case. That doesn't require much. It's discussed quite carefully in Aaron's papers. I'm going to cut a few corners to give a quick explanation. Physically, we're only assuming that the horizon metric takes the stationary form sufficiently far in the future, in the portion, in the range of times where we're studying the black hole. But we can imagine a spacetime in which the metric on some null surface has that form at all times. In fact, let h be a cut of the horizon at v equals f of x for some f. Regardless of f, since the horizon is stationary, the metric on h is just this spatial metric. Now I could consider the product of two-dimensional Minkowski space times h with this metric. And I could let n be the null surface u equals 0 in this space-time. Then I simply let omega be the ground state of our QFT in this space-time. In our analysis of Rindler horizons, we were in the case of R11, two-dimensional Minkowski space, times RD minus 2. And there was d-dimensional Poincare symmetry. But the argument only used two-dimensional Poincare symmetry. And no matter what h is, R11 times h has two-dimensional Poincare symmetry. So we can repeat the whole previous discussion and argue that if sigma is the density matrix of the vacuum for the region above a cut at V equals F, then log sigma is the same as it was before. We simply didn't use in the previous discussion any property that depended on H. I presented it as if H was flat, but we didn't really use that. So the density matrix of the vacuum is the sigma that we needed in completing the proof of the generalized second law. There's maybe one more important detail to fill in. In this picture, the initial value surface that we used had two pieces, one on the horizon and one at future infinity. Along with the state sigma that I just described on the null surface n, we could take any state sigma prime on the future infinity. So the overall state would be sigma tensor sigma prime. When we compute the relative entropies, there's now an extra term from I plus, but it doesn't depend on the choice of a cut, so it doesn't contribute in the discussion of the generalized second law.
Edward, I'm very sorry. I didn't understand what exactly the state sigma was. I'm terribly sorry. So you chose?
Well, starting with the black hole horizon.
Yeah, okay.
We just promoted it to 2 dimensions more by adding minus du dv.
Aha.
Now we have 1 plus 1 dimensional Minkowski space times H.
Right.
Then we just consider our quantum field theory on this spacetime.
Oh, I see.
Then we take the vacuum of that quantum field theory.
Oh, I see. Okay, I see. Now I understand. Okay.
Thanks for asking though, because I whizzed through it a little bit fast. You'll find a much more careful discussion in Aaron Wall's paper, where he's fastidious enough that he only claims this argument for free and supernormalizable theories, not for something like QCD. I think there are later developments that would extend it to QCD or to completely general theories. But if you look at Aaron Wall's paper, you'll see that he dots many I's and crosses many T's that I'm skipping.
Okay, but I get the idea. Okay, thank you. Thank you.
Well, I think that what I've said, even though there are points you could quibble over, I think what I've said does capture what's going on. Basically, for any quantum field theory where it makes sense, where this, yeah, okay. I think I want to leave it like this. At the end of the talk, if anyone wants to ask about dotted I's and crossed T's, we can go back to it. So any more questions on the generalized second law?
Sorry, Edward, just about that, and you can ignore this, but I mean, that GAB was the metric only sufficiently far into the future, right?
Yes, right. But where GAB was V dependent, the general second law is trivial. So all of our cuts are in the region where GAB is constant. But physically, GAB is only constant in the future. Okay, I shouldn't go back to the picture. It's taking too long. Physically, GAB is only constant in the future. But mathematically, to study the situation, physically, we're only assuming the horizon metric takes this form sufficiently far in the future. But we can imagine a space-time in which it took that form at all times.
Right.
Then we let H be a cut at V equals f of x. Okay, then we take this space-time, we took its vacuum. Its vacuum is a pure state. But since most of this space-time has the wrong metric, we don't want that vacuum. We only want to, first of all, restrict it to the null surface at u equals 0. And then we want to restrict it to the future of v equals f of x. Because that's the only portion in which this geometry agreed with this geometry.
Okay.
So what I've constructed is a density matrix above the cut that has the property we need. I did not construct a pure state in the original spacetime that has that density matrix. There isn't an elegant way to do it. I think you can show it exists using abstract arguments about operator algebras, but there isn't an elegant way to do it. What we needed was not a pure state. We only needed the density matrix above the cut. And there's this trick. We embedded the region we're interested in some other spacetime, which has an easy to describe pure state, namely the ground state. And then we took the density matrix of that pure state above the cut. Above the cut, it's highly non-pure. It's a highly mixed state above the cut. But it has the density matrix we wanted. All we needed in the proof of the generalized second law, all we needed was a density matrix, the logarithm of which had the right properties.
Okay, thank you, thank you.
The reason we needed that was that we used monotonicity of relative entropy, which is a general result about density matrices.
Mhm.
So we had to know that there were two density matrices we were talking about. We got one for free. It was the density matrix of whatever state the quantum fields were in.
Yeah.
The second one was just something we dreamed up for our convenience. And the way we dream it up was we take this auxiliary spacetime, we take its vacuum state, and then we take its density matrix in the region of interest.
I see. Okay, thank you, thank you.
Sure. Any more questions on the generalized second law?
Edward, one tangential question.
Yes.
The generalized second law followed from the monotonicity of relative entropy
Yes.
applied to the state rho and sigma, where sigma is this one that you just described. But
Yes.
can one imagine using different states for sigma and
Yeah.
proving, physically sounding theorems about black hole?
You can definitely imagine it. I don't know what's a good state to use, but you might find something. But anyway,
Okay.
conceptually, your question makes perfect sense.
Okay. Thanks.
Any other questions? Okay, I'm not sure how much time there is, but there's one more thing I wanted to explain. So I actually see in principle I'm over time, but I'm going to prevail upon the patience of the audience to explain one more topic. So by now we've spent the better part of 2 lectures discussing the Bekenstein-Hawking formula that entropy equals horizon area. As was clear from the beginning, this is a kind of thermodynamic entropy that reflects coarse graining over the black hole interior. It's appropriate if one is only making observations outside the black hole. But we found that to understand more deeply the thermodynamics of the black hole interacting with quantum fields, we need to consider the entropy of the quantum fields to be the microscopic or fine-grained von Neumann entropy. So we needed that to make sense of the Bekenstein formula, to make sense of the generalized second law, and even as Susskind and Uglum showed, although I didn't really explain it, to deal with ultraviolet divergences in the area. Now, so the Bekenstein-Hawking formula is a thermodynamic entropy formula, so it obeys the generalized second law. But the question might motivate you to ask, is there a geometrical formula for some sort of fine-grained version of the Bekenstein-Hawking entropy itself? Now, the answer was found, as I'll explain in a moment, in 2006, not by asking this question. The question was really asked after the answer was found. Oh, well, you could say in a way, a version of the question, not exactly black holes, motivated the work. So anyway, the formula that answers this question was found by Ryu and Takanagi in 2006, with a variety of later improvements, of which these are 2. Note that the Ryu Takanagi work actually was before the things I've told you about, which were the work of Cassini and Wall. To motivate the formula, we can consider a maximally analytically continued black hole solution describing an entangled state of 2 universes. I've drawn this for the anti-de Sitter case. So this is one region at infinity where there's a CFT. Here's another region at infinity with a CFT. The 2 are thermally entangled, and there are past and future horizons. I've drawn the Penrose diagram for the anti-de Sitter version, but I was tempted to illustrate the same point using the Minkowski space version. This picture is part of the black hole thermodynamics of the 70s, which I'm not explaining very much of. In particular, I was assuming that this picture would be sufficiently well known. According to Gibbons and Hawking, this picture represents 2 entangled worlds in the thermofield double state. In the tensor product Hilbert space, HL tensor H right are 1 factor for the left universe and 1 for the right. Oh, I'm missing a factor of 2 here in the exponent. That should be minus beta E over 2. I think I have it correctly here. If you construct from this pure state a density matrix for just the left or the right universe, it's a thermal density matrix. So that's essentially the story of Gibbons and Hawking from the 70s. Now, according to Gibbons and Hawking, the entropy of this density matrix is the horizon area. And for this ideal solution, it does not matter which horizon one picks or where one measures it. So in the picture, there's a future horizon of the right observer, but there's also a future horizon of the left observer. And both observers also have past horizons. So they can't see what's behind the future horizon. They can't influence what's behind the past horizon. But all these horizons are time independent or stationary. And no matter where or when you measure the horizon area and which one you pick, the horizon area is always the same. However, suppose two observers, one living on the left and one on the right, decide to disturb the system. The most general thing the left observer can do is to apply a unitary operator to h left, while similarly, the right observer can apply a unitary operator to h right. The geometry changes a lot. Now, I've drawn a picture that shows that the right observer could send a particle into the future. And similarly, the left observer could send a particle into the future. But if you think carefully about what you can do with an arbitrary unitary observer, unitary operator, you could see that in effect, the observers can also send particles into the past. Then they can create new spacetimes with arbitrary particles going out and going in roughly the way I've drawn, as long as those particles are in causal contact with the region that the external observer controls. So the observers on the boundary acting with arbitrary unitary operators can create pictures like this. For example, in this picture, this horizon grows when it crosses the red particle, so the area jumps. And this horizon actually jumps twice in crossing the blue line and then crossing the red line. So in a more general, the observers at infinity can do a lot that makes the horizon areas time dependent. Now, of course, they can change the state. They act with a unitary operator on the left and on the right. And psi was a pure state in the tensor product of the two Hilbert spaces. Acting with U left tensor U right, you'll get a more general pure state in the same tensor product. The two observers can do a lot to the system, but there's something they cannot change. They can only change the left or right density matrices by conjugation. This will not change the entanglement or fine-grained entropy. This doesn't change the eigenvalues of the density matrices. So it doesn't change the entanglement entropy or the fine-grained entropy. So there's something about the quantum state that the observers on left and right can't change no matter what they do. And it's this entanglement entropy. So you might hope that there would be something about the geometry that the outside observers can't change. If the entanglement entropy can be represented by something in geometry, it will be something that the observers on the two sides cannot change. So Ryu and Takinagi, with later elaborations, identified such a quantity, namely A over 4gh bar, I left out the 4, where A is the area of an extremal surface that's homologous to a Cauchy hypersurface of either of the two boundaries. So in this picture, the place where the two horizons cross is an extremal surface. And it's the only point on, you see, let's go back to this picture. In this pure picture, you could measure the horizon area anywhere, and it's the same. But everywhere on the horizon except one point could be influenced by an observer on either the left or right, by throwing something into either the future or the past. The only point in this picture that can't be affected by the outside observers because it's not in causal contact with them is the point where the two horizons cross. Now, where the two horizons cross, the area is non-decreasing to the future, but also to the past on both the left and right. So at that point, the area is stationary. And it remains stationary despite the best efforts of the observers on the outside. So what this space-time contains, no matter what the outside observers do, is an extremal surface in the center, a surface of stationary area, which they can't change. And so A over 4gh bar is a candidate for for a feature of the state that the external observers can't modify. So the proposal is that the fine-grained entropy is the area over 4gh bar for this Ryu-Takinagi surface, which is the extremal surface of minimal area that separates the left and right sides. Ryu and Takinagi were not originally thinking about such a pair of entangled universes. They considered a single asymptotically ADS spacetime, and they divided a Cauchy hypersurface into two parts C and D. Then they considered the reduced density matrices for the vacuum or any other state in the region C and D. Since it's a pure state, the two density matrices were supposed to have the same entropy. Well, they considered a time-independent situation, so they only looked at a spatial surface, and they said that the entanglement entropy is the area of a minimal surface L in the bulk that separates the two regions. So this was the original formulation of Ryu and Takinagi. I've explained a later extrapolation to the case of the two-sided time-dependent black hole. As we discussed in the first lecture, the entanglement entropy is ultraviolet divergent in quantum field theory, but the area of L is also, to a boundary observer, there's an ordinary theory without gravity in the boundary, and sigma of rho C and sigma of rho D are supposed to be the entanglement entropies of the vacuum or some other state in this region. It's ultraviolet divergent, as we discussed in the first lecture, but the length of L is also divergent. And the claim is that cutoff versions of the entropies match cutoff versions of the areas or lengths. So the RT formulas had a big impact from the beginning, and the impact has only grown as people have become more aware of the importance of fine-grained or microscopically defined entropy, partly because of the developments I've explained in these two lectures. So in summary, today we discussed the generalized second law, and we learned that, like the Bekenstein bound, to understand it well requires interpreting matter entropy to be the fine-grained or von Neumann entropy of a density matrix. And I gave at least a few hints about the fine-grained version of the Bekenstein-Hawking formula, of which the earliest version is due to Ryu and Takinagi. Thank you.
Thank you very much, Edward, for a wonderful talk. Let's all unmute and thank Edward. Questions? Do we have questions?
I have a question.
Go ahead.
So, it is somehow related to the last talk in the sense of the ultraviolet divergence of the area law formulas. Now, on slide 59 of the first talk, you had a very important formula relating U to the asymptotic time, essentially by an exponential. And basically your point was that, you have to enable extreme short distances in the U coordinate in order to be able to, derive these formulas. And that worries me because it means that we are dealing with extremely high energy.
We do not have to. Let me give you some good news.
Yes.
Well, it depends on the size of the black hole, but that derivation only required starting at distances small compared to the size of the black hole. So if you have a solar mass black hole, we could do that derivation where the short distance is a millimeter, which is in a region where we're quite confident about quantum field theory.
I see. The just a small follow-up is that if I take that formula and make an analytic continuation of time to Euclidean time, then all this discussion of ultraviolet divergence simply disappears. Is there something?
It can't completely disappear because the answer, which is the area over 4G, does have an ultraviolet divergence. What would happen is the following. Let's go to Euclidean space, as your question suggests. So then we have the Euclidean black hole. It has a classical action, but now suppose we calculate the order h bar correction to its partition function. Order 1, sorry, the classical action is 1 over h bar. So now we're computing now we do the path integral of matter fields. So we calculate some determinants. Those determinants are divergent. They have a divergence proportional to the volume, also a normalization of the cosmological constant.
Yes.
Assume we cancel it. but they also have a divergence proportional to the Ricci scalar. So that renormalizes Newton's constant. And it renormalizes the coefficient of the area term. So what Susskind and Uglum showed, and it's an extremely simple argument, as you might expect from Susskind, and quite illuminating. It's very simple, but it does require things that I actually haven't explained. What they showed is that the coefficient of the ultraviolet divergence in the entropy is the same as the coefficient of the scalar curvature term in the ultraviolet divergence of the partition function.
Okay. So it is extremely important that one really has to consider these two quantities together, the entropy of the quantum fields and...
Yes. Well, the Bekenstein-Hawking story makes sense if you ignore quantum corrections, but if you consider quantum corrections, the two together are better behaved than either one separately. The entropy in particular has that horrible ultraviolet divergence that my first reaction to the Ryu Takanagi formula personally was unenthusiasm, because I just couldn't believe that a quantity with such a horrible ultraviolet divergence was really useful to study. But that view hasn't held up well. But anyway, an important fact is that in the bulk, area over 4G plus the entropy is better defined than either term separately.
Thank you.
Sure.
Edward, could I ask a question about the early part of your talk?
Sure.
You said theta cannot become, when you're explaining the classical Hawking area increase theorem,
right.
You said theta could not become infinite, it could not diverge. Now, does that statement assume that no singularity develops on the horizon classically?
I think in Hawking's original presentation it did, but you can avoid making that assumption. In Wald's book, he explains how to make the argument without making that assumption. And in my notes, I explained my version of the proof of many of these things that use the Ricci-Dore equation in my notes on light ray singularities and all that. So either in Wald's book or else in my article, you can find a careful explanation of this story that fills in the details I skipped in the lecture. Exactly why theta can't go to minus infinity and why you do not need to assume the horizon is smooth.
I see.
Although you don't, let me tell you something. Although you don't need to assume the horizon is smooth in this argument, in general, to understand black holes, you do need to assume that the region outside the horizon makes sense, which people usually summarize by saying it's smooth, but that assumption might be too strong. But if you assume not, you need something similar to cosmic censorship to make any useful statement about black holes. But again, you can read that in Wald's book or in my article.
Okay, thank you.
Sure.
Hi, Edward. I have a simple question. So in Wald's paper, you said he focuses on free and super renormalizable theories. What do we get by considering those? Because the argument you gave seemed more to be on the other end for conformal and asymptotically free theory.
Well, my argument certainly applied to free and super normalizable theories. I tried to state it as much as possible in a way that didn't assume that. If you are fastidious, what Wald worried about very much was whether it's truly physically sensible to define a quantum state on a null initial value surface. So does null quantization make sense? And
I see.
For free or super normalizable theories, you can be very explicit in proving that, well, for free theories, you have explicit formulas. And for super normalizable theories, they're close enough to free theories that that's good enough. So for those theories, null quantization definitely makes sense. For other theories, you should worry about the extent to which null quantization makes sense. And
I see. So QCD is a theory where we should worry whether null quantization makes sense.
Yes. I believe it's possible to make these arguments without assuming that null quantization makes sense, but it's longer.
Okay, thanks.
If I would ever write this up, I would try to write up a version that doesn't quite assume that null quantization makes sense.
Mhm.
Edward,
Yes.
sorry. So thank you for such a beautiful talk.
You're welcome.
Just to, thanks a lot. So just to ask you, I mean, this is a general question. Of course, the generalized second law you proved was also for the event horizon of the black hole, like the original. And there's always this, what is it, teleological aspect to the discussion, because we don't know where the event horizon lies till we know the entire history of the black hole.
Yes.
Is it possible that there is a more local version where we think about, if not the apparent horizon, something like that, which would be more in line with the usual laws of thermodynamics, which don't require the entire history?
There might be, I'm not sure. We can discuss a little bit of it. First of all, there's a literature where people try to do it. I can't remember what to say, so I might be forgetting things that are well established. Although I doubt they're well established and as precise as Aaron Wall's discussion. You might have to compromise a bit, but so first of all, what we could do for your question is to consider two cuts of the horizon. Well, yeah. Yeah, okay. Instead of a null surface that's stationary up to time infinity, we could have a null surface that's stationary only in a range of times.
Okay. If I may, can I ask a small extension of the same question?
You can, although I was stumbling in answering that question. I'm forgetting what's been done, I'm afraid. So I'm not sure if there's something on point that I should be quoting. I think there are at least some partial results known. Go ahead with your question.
Yeah. So there are these dynamical horizons that are being developed in GR, where the horizon is considered to be local.
Well,
instead of the event
the horizon.
Yeah.
Well, it makes sense, but the question is, can you prove a generalized second law by, or at least by similar methods? What can you prove?
And in these horizons, I think the horizon metric is time dependent.
Well, if the horizon metric is time dependent, then there won't be an interesting question along the lines that we discussed.
Yes.
Because, well, if you want for something to be called a horizon, I think the area should be non-decreasing. People who discuss, try to give a local characterization of the horizon, I assume they mean a null surface, at least. Then what do they assume about the time dependence of the area?
So, sorry, there was this proof by Busso and Engelhardt about the so they consider the future and past holographic screens to be the replacement for event horizons.
Right. Okay.
And on those surfaces, the area is monotonically increasing for future and decreases for past. So in that sense, you can consider those to be
what that was defined with the classical definition of the entropy, was it not? Or did they take into account the quantum corrections?
Not the quantum corrections. It was for the classical.
Okay. Okay. Well, I don't know a good setup. Sorry. Well, literally, I don't know a good setup, but I don't feel I remember or know everything that's in the literature for a good analog of the question we discussed in the lecture involving the quantum corrections for surfaces only locally stationary. But I'm not at all sure. I don't mean to make a negative statement, except that I don't know what to say right now.
Okay.
The reason I think you might be able to say something is that if you, instead of considering the whole region to the future of this null cut, if you consider a region sandwiched between two null cuts, you can still say something simple about the density matrix of the vacuum in that region. And so that would be an ingredient in a proof of what you're asking for. I don't want to say anything about whether the rest of the proof works. It may be known, as I say, but not by me at the moment.
Yeah, I see. Yeah, the fact that that expression was the density matrix of a state, that didn't, somehow I didn't follow things enough, Edward, sorry, excuse me. I mean, at some point you were taking that state as defined asymptotically, but was that necessary or?
I never took it state defined asymptotically. One state was the actual state rho we're interested in.
Yes, that I understood. And
the other state is the state that would have been the vacuum if the system had been time independent for all times. And then the system actually wasn't time independent for all times, but we took the vacuum of the other space-time, and then we took its density matrix in the region of interest.
yeah.
So it wasn't asymptotic, it was to the future of a cut.
I see. So that's why you're saying perhaps it might be possible to extend this just by sandwich.
Well, I'm just saying that the vacuum for a region sandwich between two cuts still has a simple density matrix.
Yeah, yeah.
And I'm forgetting what's been used in the literature using that. So if I remembered, I probably could answer the questions better.
Okay, okay, okay. And then a very quick follow-up, sorry, which is, assuming we go with the event horizon, is there a bit of an issue if we are allowing for evaporation, then eventually the black hole is going to get to be a Planck size. So what precisely do we mean by the event horizon?
Well, that question is beyond the scope of this lecture, where we only considered the order h bar correction. So literally, we took a classical horizon and discussed the order h bar correction to it. Now, see, okay, we had this equation. I wrote the solution here, but you could ask how A behaves in the far future.
Mm-hmm.
And the answer is, so first of all, so you should have to ask what TVV behaves like in the far future. So the answer is the TVV in the far future goes as 1 over v squared, assuming that what you have in the far future is, ignoring the, before the back reaction becomes big, but in the far future. So after a long time, but not so long that the Hawking radiation is a big effect, TVV is of order 1 over v squared due to Hawking radiation. If you plug it into this, you learn that A grows logarithmically in the future with a minus sign. So that describes the shrinking of the horizon due to Hawking radiation.
Right.
So in this approximation, you get minus h bar log v. But at exponentially large v, that becomes a big effect and this computation breaks down. So we computed the order h bar term, but that approximation isn't really valid for all times. As we discussed in the first lecture, v is the, v is e to the minus the time measured at infinity. So this minus log v actually means, from the point of view of an outside observer, that the horizon is shrinking linearly in area.
Right. Okay. Yeah. Okay. Thank you very much. Thanks a lot.
Sure.
I had a question about the renormalization of the Newton constant that you mentioned. So in your discussion of the quantum correction to Raychaudhuri equation, so in that you didn't take into account any renormalization of the Newton constant, did you? I mean,
not with the F higher order, right? So we already were looking at terms of order.
Okay, got it. Because it's 1 over h bar, and I see it would be.
Well, let's, if we can find the Raychaudhuri equation, TVV was of order h bar. We evaluated this equation in order h bar.
Right. Okay, I see. So you're saying that if G has an order h bar correction, then that would come at order h bar square.
Yes.
Got it. I understand. Thank you.
Sure.
I have a question. So what geometric quantity captures the von Neumann entropy of, let's say, a one-sided black hole in a pure state?
If it's in a pure state, the von Neumann entropy is 0.
Yeah.
And the way that it's explained with the Ryuta-Kinagi formula is that if you have a black hole in a pure state, let's look for a picture of one. let me try to find the Schwarzschild, sorry, the Penrose diagram. Okay, here it is. You can see my cursor, can't you?
Yes.
Okay, so, well, this is drawn for Minkowski space, but it would be similar for an anti-de Sitter space. We have a region at spatial infinity out here. We're supposed to take the minimal area surface of smallest area that's homologous to the boundary. But the boundary is homologous to nothing for a collapsing star, because there's no topology to hold it up. So the Ryu-Takanagi surface is the empty surface for this type of case. So that goes with the fact that the von Neumann entropy of a pure state is 0.
Yeah. Thank you.
Sure.
Are there any more questions? If not, let's thank Edward again for
I have a question.
Okay, go ahead.
Could you comment a bit about how to interpret like renormalization by adding area by 4Gs when you don't have gravity in the theory?
Don't have what? Don't have what? Sorry.
When you don't have gravity in the theory, like when you naively think of G goes to 0 or something.
Well, even if you don't consider quantum effects due to gravitons, matter fields cause an ultraviolet divergent renormalization of Newton's constant. So just for quantum fields in a background spacetime, to make sense of A over 4G, you have to renormalize. You can't just use the classical action because the partition function of a quantum field in a background spacetime is divergent. The divergences renormalize the parameters in the Einstein action, both the cosmological constant and G. So once you're doing quantum theory in a background spacetime, you have to at least do the renormalizations that requires.
Okay. So does it make sense to wish that one should come up with a definition of the entropy where you naturally get these terms rather than adding the area term by hand to renormalize it?
Well, I'm not sure I'm understanding the question correctly. One question could be,
I'm saying that so the way we do it, you would calculate the entropy by doing QFT, and then you add the area by G Newton term by hand, or in a theory without gravity, you would say add the do what you said now, as in add the some analogous term which captures the renormalization. But instead of you get. Sorry, go on.
I believe the question is, what are we doing when we add the A over 4G term by hand? In what sense is it an entropy?
Yeah, so does it make sense to or what should I look for if I want to come up with a definition which gives it to me from the beginning rather than arguing for it, say a posteriori by saying renormalization works nicely or something.
Well, what you're drawing attention to is the main question about the subject. The main question about the subject is, what's the theory in which A over 4G actually is an entropy? And the main reason for interest in the subject is the hope that black hole thermodynamics is a clue about understanding gravity more deeply. So
I was thinking more naively in the sense of can I come up with a deformed version of the entanglement entropy definition which say includes these curvature corrections or whatever.
I think you're going to find out that to do that, you need a good quantum theory of gravity. That's at any rate what most people have believed ever since black hole thermodynamics started in around 1972 or 3.
So does it come up naturally in string theory?
The answer is that in either string theory or any other framework, there isn't a good understanding of the sense in which A over 4G is an entropy. So in string theory, there are computations, for example, for supersymmetric black holes, where you can count the quantum states and show that the answers you get matches with A over 4G. But there isn't an a priori explanation of why A over 4G is an entropy.
I'm maybe looking for more a naive answer is there a naturally motivated deformation of rho log rho, which gives me that?
I'm pretty sure that's the wrong question. I'm pretty sure the right question is, what's the theory in which A over 4G actually is an entropy? That's what all the experience of the subject shows, that the laws of black hole thermodynamics are the ordinary laws of thermodynamics applied to an unusual system that we're not that familiar with. And the key question, as identified by Bekenstein, Hawking, and many other people since then, is what is a theory in which A over 4G actually is an entropy? To be honest with you, I didn't explain that. When I introduced black hole thermodynamics in the beginning of the first lecture, I did the minimum that was a basis to make sense of what I really wanted to explain, which is the role of fine-grained entropy. So I didn't explain what I just did tell you, that the central question of the subject is to understand what really is meant by A over 4G as an entropy. Or maybe I did briefly, but I didn't make a big point about it.
Thank you.
I would say the following. We don't have any general understanding of what string theory is. We also don't have any understanding. The story of black hole thermodynamics is probably telling us there's something general about gravity we don't understand. Now, if you're an optimist, you'd hope that the general thing you're missing about string theory and the general thing you're missing about gravity would somehow make contact with each other. Will it happen? I don't know. But anyway, that's what you'd hope if you're an optimist.
Okay. Do we have any more questions? Okay, if there are no further questions, let's thank Edward again for a wonderful talk and answering all our questions.
Thank you.
Thank you so much. Thanks, Edward.
Thanks all of you and be well. And
Thank you.
Sorry, Edward, one request. If you could send us the slides for the talk, that would be great. We would put it up with the recording.
Okay, sure. Okay. All right. Bye-bye.
Edward, you really cheered us up at a time where we are feeling a little down. Especially, thank you so much for coming back also and taking so much effort. Thank you very, very much.
Well, it's my pleasure. Thanks for the invitation. And
thanks so much, Edward. Thank you.
Okay. Bye-bye. Be well.
Bye.
Thank you. Bye.